In this section, we're going to take a database management system and we're going to break it down into constituent parts. We're going to look at each one of the parts and we're going to explore what its functionality is and how it interrelates with all the parts around it. When we talked earlier about database history and we talked about early database systems just not being up to snuff with what we have currently, we're going to use this as an opportunity to explore those differences. So for example, I mentioned that current relational database management systems usually manage their disk disk access, whether it's reads or writes, and they don't go through the operating system, file system to do that, right? And that I said that was advantageous for speed reasons, but here we're actually going to dive into what makes that work. How does a buffer manager act in a way to manage memory and make sure that we have things available to us in memory, which is much quicker to retrieve it from than from disk, and at times we need it. And when we do need to go to disk, how do we mitigate some slowdowns there, right? So how in the real world does all of these components come together to give us a really, really good experience? Another kind of point here that I just want to make quickly is that this is specific to relational database management systems. NoSQL database management systems may or may not use some or all of these features, but this is specific to relational ones. We're also working off of what is in the book here as our backdrop. So if you go to page 6 of chapter 1 in the book, you will see this map here, and these are the different components that we're going to go through, and I'll describe in a moment the path that we're going to take. But first I just want to note that if you haven't already read the section in the book on this, I strongly encourage you to do so. What we're going to discuss here will go hand in hand with what is in the book. I also want to point out that I took a slightly different approach to how I broke out the sections. The book jumps back and forth a little bit more, and while I'm not saying that one method is necessarily better than the other, I try to stay more linear in approach. As you'll see, I broke it down first by the two major categories of interaction, the user interaction and the database administrator interaction, and then further within the user interaction, there's kind of the main query, and then there's transactions, and we'll talk about both of those. But those are the kind of two-tiered breakdown approach, and I'll show you in the slides where you can see those in a moment. But once we have that kind of established, you'll see the path is pretty consistent. The book, however, does a little bit more jumping around. It'll start talking about, say, like the query piece, and then it'll jump back to the transactions and kind of do a comparison between them. And all the while, it's kind of talking about each one of these functional components in bits and pieces, and you kind of have to piece it together. Now, you might find one way better than the other, but at least this way you have both options. So I do strongly encourage you to also read the text in the book. It should coincide very much with what we are doing here. And you'll see here in my slides that I've broken apart the parts that I'm talking about and taken little screenshots of the map. So you can see here, like when we're talking about the different paths the user can take, it's right there. And then once you're doing the query, I have the three major parts there. And you'll see that when we talk about storage managing, here it is here. So I tried to break it up into the slides. So I said that there's the kind of two major decision points that I use to break this apart. The first is, as I mentioned, the database administrator use case and the user use case. And then within the user use case, we have two pieces. We have query processing, which is denoted with a star along with transaction processing. So when we get to these slides, you'll see I have a star here in front of query. And then later, when we get to transaction, I have a star there so that you know that we switched over to that. Both of those are within the user commands, and DBA commands is a much shorter section, so we're going to start there, but it's really just one slide. So that one's pretty straightforward. So with all of that introduction said, let's jump in. So the sources of commands is how we're going to break apart our attack on dissecting this thing. And they coincide with basically two things. You are either creating and managing your metadata or your schema, which is a database administrator role, or you are using it in some way, which means that you're a conventional user. And this would be any of your select, update, delete, that kind of stuff. And that would be a conventional user approach. So we're first going to look at the database administrator piece, since that is by far the shorter of the two, and then we're going to jump into the user side. On the database administrator side now, the commands we're issuing, we've talked about before, these are our data definition language commands. So again, all of these commands are specific to creating a schema, altering a schema, managing access to the schema, like a grant for a user, something like that. All of this information is stored as what is known as metadata, which is data about the data. This is where we store information that describes how we're actually going to store the information that we want to store inside the database. So if I have a user table and it has my first name, last name, and age fields, the metadata would include the size of those fields. It would include the data types of those fields. It would include the number of fields that make up my user relation. It would include how many relations are in my database. All of this is considered schema information. And anytime you are changing or manipulating schema information, you are using data definition language to do so. And again, this is only done by a database administrator. Now, in contrast to this is conventional user commands. Now, this is data manipulation language. Anytime you're doing a select, an update, a insert, or a delete, this all falls into this category. It does not affect the structure of the database. I can't change my user table structure with this, but I can affect the content. I can delete a user, I can add a user, I can find users, right? All of that falls into the data manipulation piece. Now, it's important to also just kind of point out that a database administrator can also be using data manipulation language. And they're doing so primarily as a user. They might be an extremely well-privileged user. In fact, they might be the most privileged user who uses the database. But anytime a database administrator, say, is just doing updates on individual records, they are in fact interacting with the database as if they were a user. So that's an important thing to point out, that just because your title is database administrator doesn't mean that you can't be using data manipulation language. Data manipulation language now, we're going to further break down into two pieces, and this is where we're going to spend the bulk of our discussion time here. The first is we're going to look at is query processing, and this is just looking at how every single query goes through the system, how we break it down and understand it into different pieces, how we optimize it, how it actually gets executed, how information gets from disk and back out. Transaction processing is now how we deal with grouping of queries. You will learn more about this, but it is going to be common that we have to guarantee that a group of transaction or group of queries that form a transaction will be completed holistically. So we need to be able to say that in order for this transaction to be effective, we had to enroll a user in a course, update the course with the number of available seats, change some other information in another table that's related. And those three things have to happen together. If they don't, then we have to throw away the whole thing. That's the concept of a transaction. So the first piece of this is looking at how each individual query is handled. And then the second is looking at how we might group those queries in order to achieve a situation where our data is always compliant with where we expect it to be. And we're going to wrap all of this up by talking about the idea of what's called the acid test, which basically is the properties we expect of our relational database management system, that it can ensure that our data is consistent and meets our expectations, and that there's not going to be a situation where there can be an error and our data can be out of sync with where we expect it to be. So let's jump in with the query piece first. So the first piece I want to look at here is the breakdown of what actually happens when you do an individual query. And there's 3 steps I'm going to talk about first, and then we're going to talk about more of the storage piece of it, of how we manage storage and memory. But this you can think of more similar in nature to if we were compiling, say, a regular programming language like C or Java or something like that, where you're taking your source code and making it into a binary. You can almost think of this like that, right? So we're going to take our SQL, which is our high-level, very abstract language, and we're going to take the queries that we generate using our SQL and turn those into actual pieces that we're going to request from memory or disk. And that's what query processing is all about. So the first piece of this is our query compiler, and its job is to parse and optimize the query. There's 3 kinds of sections that it uses to do this. The first is the actual parser, which is going to take the query itself. So say you have a query like select first name and last name from user, where user ID is less than 100. That's a very simple query that's going to return hopefully the first 100 users if they all have concurrent IDs, and give you their first names and last names, right? But it's going to break that down like the where clause and the 2 fields that you wanted from the table, and the table name itself is all going to be broken up into a tree type situation that it can use to identify the constituent parts. What are the constraints? What is the piece that we're querying from? And what are we hoping to get? There could be, of course, more complex information involved, especially if there's joins. And we'll talk more about that later in the class. But this information is now going to be passed to the query preprocessor, which actually does semantic checks on the information. And it turns that tree into algebraic operations called a query plan. That query plan is now passed to the query optimizer. The query optimizer's job is to take it and decide what is the best possible way I can go about getting this. In order to do that, it uses things like metadata and indexes and statistics to decide. We're going to talk about that more later, but for now, just accept that the query optimizer's job is to make sure that we're going about our query in the way that gets it done as fast as possible. And how it does that is related to some of these pieces a little bit further down. So now those algebraic expressions are now passed down through to the execution engine, which then issues a series of requests for the kind of smallest constituent parts of our data. So when you look at, this is very dependent on how the database management system actually stores the information, but the execution manager's job is to take each part of that query and break it down into individual like tuples, basically. They're typically records that are within the relations or the tables, and the individual pieces, like we said, where ID is less than 100, right? So one of those tuples would be that particular piece. Another might be the actual fields that we wanted to get back, right? Like the first name and last name. And this is going to be specific. The job here of the execution engine is to break it down into the pieces that then relate to the specific ways in which we store that information further down. Now, the resource manager also has information about indexes and other things that will speed up execution. Now, indexes we haven't talked about in depth, and we're going to get more into them, but I'm going to brush on it lightly here, just to kind of show how this takes effect. So an index is the idea. Let's say you have an application and it has a search page, and you search your users by their last name, right? So it's a very commonly used page. You want to speed this search up because you get thousands of searches a day, and you want them to be fast. So what you can do is you can index, put an index on the last name field of the user table. And what that means is that the database management system will keep an in-memory representation of that table that is easy to look up by last name. So anytime you say have a query come through that says select, user's first name, last name, ID, other information, where the user's last name equals, and you're going to pass some last name in, it will, instead of necessarily like going to disk, the resource manager will be able to return from this index, and that very quickly return the information that you need based on common constraints. So these are mechanisms that are put in place to significantly speed up how fast this takes. Now, once all of that is done, once the execution engine and the record manager have been used to find the most efficient path to get us the information, we still need to actually get the information. And where we query to do that is a place called the buffer manager. Now, the buffer manager is a lot like a cache controller. Now, for those of you who may not have had, say, like an architecture course, or it may have been a while and it's not something that's fresh in your memory, I want to just touch on it briefly because it's a good analogy of exactly what a buffer manager does. A cache controller in a computer is a mechanism by which, if the CPU needs data for its registers to do some computation, right, it looks to the cache controller to say, is this information in cache? Cache is a smaller but fast chunk of memory that is close to the CPU and is a lot easier for the CPU to get to and faster. So you have your CPU, it does billions of things a second, but accessing RAM is slow. It might take 200 clock cycles for the CPU to ask for some piece of data from memory and get it back. That's an eternity, for the CPU. It could have done 200 things in that amount of time, right? So what we do instead is the CPU calls to the cache controller. The cache controller says, I have this faster space of memory here because it's SRAM, not DRAM, and it's closer to the CPU. And maybe it only takes like 10 or 20 cycles for the CPU to call a cache and get something back, which is, 10 to 20 times faster than our analogies statistics before. And the cache controller's only job is to say, do I have this thing in cache? And if I do, return it to the CPU. And if not, then go to memory and get the thing. But you don't just get the thing, you get the memory block that it is in. It's called a cache line, and bring it back to cache. And then now I have an algorithm called recently used where I decide what I'm going to kick out if cache is full, and I put that thing in. Now, this is very, very, very much how a buffer manager works. A buffer, basically is just content in memory that we can get to and use, right? So if it doesn't exist in the buffer, then we're going to have to go to disk to get it. And that's what the buffer manager's job is. Check, see if this thing is in memory, manage what information is in memory. There's a lot of tuning you can do with this. If any of you have ever worked with Oracle or some other higher end database management systems, there are lots of ways that you can tune what tables and what views and what content is actually managed in your buffers. So this is probably your single biggest asset when you're trying to manage the speed of how well your database management system performs, is how you tune your buffer manager, how much memory is available for it to use to cache things, so it does not have to go to our next step, which is the storage manager, or at least it goes as infrequently as possible. So if the buffer manager does not find something in memory, then it does in fact call down to the storage manager. And the storage manager, the job of the storage manager is exactly what it sounds like. It manages getting information from storage. So the blocks and all that, I'm going to come back to the other slide in a second, that are on the disk, it will bring it back. So if you have, a call for something and you don't have it in a buffer, you will get usually that entire sector off the disk and bring it back. Now, what's interesting about the storage manager is because database management systems have control over their allocated space on disk outside of the file system, this is in fact the file system, so to speak, of the database management system. And we don't want to have to think about the nuance of how our tables are actually stored down into ones and zeros, but the storage manager does that, right? And this is the piece that does it for us. And it knows how to best allocate space on that disk to make sure that it can, do updates and allocate new space when it needs to, all very fast, right? So this, because it's highly tuned to the specific needs of dealing with data at large scale that we have to do in a database management system, this is much more efficient than relying on the operating system's methods to do so. The slide I came back to here, or that I skipped, that I'm coming back to now, is the types of data that we manage with the storage manager. So we have the database contents itself. We have metadata, which again is our schema itself. We have log records, which are logs. We're going to talk more about that in transactions in a moment, as far as like what we can use our logs for. Statistics is information about the data properties, like its size and relations, and the indexes that we talked about before, right? Those are helping us keep everything fast and efficient. All right, so those were the individual queries. So let's talk now for a moment about actual transactions. So transactions, remember we said, are queries that are grouped together. And the key here is that we have to execute them atomically. In other words, we have to say if there's 3 things that need to happen, they all happen or none happen. And that's the key. It's an all or none proposition. The other big thing we have to guarantee is that they happen in isolation from other transactions. Now, an important thing to point out here is not that transactions can't happen at the same time, because if you have a multi-core, multiple CPU system, you don't want to say, I have 8 CPUs, but only 1 transaction can happen at this moment because that's the deal and nothing else can. What's the point of having all this horsepower, right? Well, the key here is that transactions have to happen as if they are isolated from other transactions. So there's 2 pieces to this. One is that we have to maybe look at the transactions and see which ones we expect will have effects on others. And if they are going to have effects across, like if transaction A and transaction B touch the same table information, then we do have to stagger them, right? But if we look at them and we see no correlation there, they're doing 2 completely unrelated things, then we can in fact allow them to run through different CPUs at the same time. That's perfectly okay. There's also a situation called deadlock, which we're going to get to in a moment. And if deadlock occurs, which means that 2 transactions not only affected each other, but basically one is talking to a piece that another one needs, and the second one is talking to a piece that the first one needs, and neither one can progress because they're kind of stuck in this endless loop, then we have to be able to undo that, right? So we have to be able to guarantee that in addition to them not stepping on each other's toes, if they do step on each other's toes in any way, shape, or form, we can undo one of the transactions. Those are the 2 pieces that we need to guarantee for this to work. And this is done by our transaction manager. So our transaction manager accepts commands from an application. Now, this could be just the GUI that you're using to issue queries from, or it could be your actual application that is connected to your database, right? That is create prepared statements or something like that. The transaction manager can then run these transactions and ensure that they are durable. The idea here is that the effect of a completed transaction must persist even if the system itself fails, right? So this is where the log is going to come in, and we're going to talk about that more in a moment. But if, say we said before there was like 3 things in our transaction and they all had to happen. If thing 1 and 2 happen, but thing 3 doesn't complete, we need a mechanism to do what's called a rollback. We need to be able to say, okay, thing 3 didn't happen. We don't know why. It doesn't matter. Maybe someone pulled the power, who knows? So we're going to check to make sure that the database is in a consistent state from the outcome of 3 if something was half written or something like that. And then from parts 1 and 2, we're going to roll those back. We're actually going to have recorded what things looked like before they happened, and we're going to go back to that state as if this transaction never happened, right? That's the key. So this is an all or nothing proposition, and the transaction manager ensures that the transaction is durable, that we do in fact live up to those pieces. Now, the transaction manager uses these 2 mechanisms to accomplish this: the login and recovery piece and the concurrency control. So we talked about the concurrency control before when we talked about isolation, right? So this is our scheduler, and it ensures that atomicity and isolation of transactions. And this is the piece that looks at the incoming transactions and says these 2 can run concurrently, that's okay, or deals with the bad things that might happen if they do run concurrently and they shouldn't have. So it's important to note that not all database management systems are smart enough to know exactly when to run them concurrently and when not to. It's a philosophical difference on how you're going to manage that. There might be more overhead in making the decision than there is in the probability that something goes wrong and dealing with cleaning up the mess, right? So you have to kind of make those decisions, and that is made by the people who implement the concurrency control manager in your database management system. The other piece is the login and recovery manager, and this is the one that is responsible again for the durability of those transactions. So the way this works is, say I have that transaction for 3 things like we described before. What I do in the log is I say, okay, I have a transaction, transaction A. It has the 3 things and it lists them out. Then when you start thing 1, it notes in the log that thing 1 started. And then when you finish thing 1, it notes in the log that thing 1 finished. Then query 2 starts and it notes that. And query 2 finishes and it notes that. And query 3 starts and it notes that. But query 3 didn't finish, right? Something went wrong. So now when we start back up and we review the log, now the recovery piece can look at it and say, oh wait, this transaction didn't finish. I don't have part 3 finished. So it can check transaction 3 because it knows that's where it hung up. Then, and all the previous data states are recorded in there as well. And then it can use those to roll back the second and first piece of the transaction and get us back to a stable state. And then if you have the transaction to try again, you can go ahead and do that. So those are the 2 kind of underlying mechanisms that it uses. Now, the scheduler, which is just another name for the concurrency control piece, the scheduler does its job because it has something called a lock table. Now, a lock table is stored in memory, and it's a just table that keeps track of what is currently being accessed or written to in the database currently. So, if you have a user table and you're updating my user record, some database management systems can do row level locking, which means like you only have to lock the actual row you're changing. Some have table level locking, which means that if I'm altering a user in the user table, the entire user table itself is locked, which is obviously not as good. But this basically allows you to always know that you have consistency in your data, right? So if you're updating my last name and you lock my row and somebody else is trying to query, they're going to have to wait until the lock is released. So they won't see the name in the old form, they'll see the name in the new form, and hopefully the lock gets released quickly, so they don't have to wait a very long time, right? But that's the idea of how a lock table works. And this is used by the concurrency control manager to ensure that things happen only in correct order. Now, deadlock is that situation I described before, right? So deadlock is the idea that a transaction can't proceed because it's being held on to by another transaction. So two things are locked and one is needed on both sides, and it kind of forms this loop. You know, one can't proceed because there's a lock on for the second one, and the second one can't proceed because the first one has something locked. So the transaction manager has to detect these things, and what it does is it basically chooses a transaction. Now, how it does that is up to its internal algorithm. Maybe it's random, maybe it looks to see which one got further along, maybe there's some kind of importance, who knows. But whatever mechanism it uses to make that decision, it then cancels one of the transactions. It rolls it back. So wherever it was, it stops it, just like we talked about when we were talking about the logging and the durability, and it rolls it back. It undoes everything that it does. This allows the first transaction to continue through and finish, and then it can go ahead and rerun the second one. This slide we already talked about, so I'm just going to go through it quickly. We already touched on it in the previous slide. This is the log and recovery manager. This is where we're writing out those logs, right, to keep track of everything. So if we have to undo something, we can. And it allows us to preserve consistency of our database, which is absolutely paramount. And now that brings us full circle. So a core thing about doing transactions in a database is that we want our transactions to meet this ACID test. And the ACID test is an acronym, and it stands for those terms that I kept bringing up as we were going through: atomicity, consistency, isolation, and durability. Atomicity means that we can guarantee that the actions are being performed completely, that from start to finish, all of them get done. Consistency means that we have constraints and we're using them. So we know that our data is going to be as expected. It's not going to say, have, a 52 character name in a space where we only allow 50. And we know that a person who's looking up information at the same time we're trying to change it will have to wait until we're done changing it, so they don't see a result that is inconsistent with what the result was supposed to be once that time had passed, right? Even though the read operation is quicker than the write, they're going to have to wait for that write operation to complete. Isolation is the idea that a transaction must be executed as if no other transaction is executed at the same time. And that as if is absolutely crucial, because remember, we do want to take advantage of multiprocessing systems, and we do want to make them go as fast as possible. And to do that, we do need to have transactions happen concurrently. But we need a mechanism to deal with what happens if that fails, right? We need a safe way to ensure that we can roll back information and try again. Durability is, again, the effect that we're not going to lose any of these transactions once they are completed, which is the big caveat there. If they get halfway through, we're going to use that rollback process to undo them if something crashed or went wrong. And this is where our logs come into play to ensure that. This ACID terminology, I guarantee, is something that we're going to see again. It's extremely important conceptually to what relational databases give us.